Hi. So in this video, I want to introduce the Hall effect, and that's going to be the main part of this video. But I also want to talk a little bit about photon absorption by semiconductors, so optical properties, and the difference between direct and indirect energy gaps in semiconductors. Before we get to that, however, there was an interesting question that came up at the end of class today, and that had to do with this discovery of a superconductor that becomes superconducting at room temperature, which is a huge breakthrough, of course, a huge leap. But the caveat there was that this new superconductor doesn't do that, doesn't become superconducting unless you apply an enormous pressure. So only at very, very high pressures do we see that superconducting transition. At ordinary pressures, it's just a regular material. So that brought up the question about the role of pressure in general. How does pressure become important in the context of semiconductors? Does it matter? Can we apply pressure to a semiconductor and change its properties? That's an interesting question. And the quick answer is that we're not going to see anything nearly as dramatic as in this recent discovery on superconductors, because there the pressure was actually instrumental in causing the phase transition into the superconducting state. Now, it's with enough pressure applied, we could induce that superconducting phase transition, that rearrangement of the state of the material, the macroscopic state of the material, to support the superconducting state. So a huge reorganization of the entire substance. With semiconductors, we're not going to get that by applying pressure. But we are going to change the energy levels around a little bit. And in general, we can say that the the band gap energy increases a little bit with pressure. So most people are maybe familiar with a temperature dependence of the band gap, which is also a small effect. But as the semiconductor is heated up, usually the band gap shrinks a little bit because the crystal itself expands, thermal expansion, and so you're going to get the lattice spacing to increase just a little bit with temperature. And so the band gap does depend on the lattice spacing. And so inversely now, if you're going to apply a large pressure, you're going to decrease the lattice spacing, and therefore you're going to go in the opposite direction with the band gap, namely you're going to tend to increase the band gap. So there is that effect. Okay, so the next order of business is to look at direct versus indirect semiconductors. And of course, we have those two very important examples of gallium arsenide being a direct, having a direct gap, and silicon having an indirect gap. So just to remind you, this is sort of what we had looked at before. This is sort of the simplified, let's say, band structure of gallium arsenide. And here then is the simplified band structure of silicon. What's interesting here is that the bottom of the conduction band is here at k equals 0, and the top of the valence band here is also at k is equals to 0, and there is an energy difference of about 1.52 electron volts. So the E sub g, the gap energy here, is about 1.5 electron volts. But the valence band and the conduction band sort of are facing each other in k space, okay, for gallium arsenide. But that is not the case for silicon. We said there the top of the valence band is sort of at the origin, again in k space, a point sometimes referred to as tau, but the bottom of the conduction band is at a different point in reciprocal space at a point sometimes labeled x. Okay, and so the band gap, the difference here between the top of the valence band and the bottom of the conduction band, is about 1.17 electron volts at low temperatures. And we see that goes down just a little bit, sort of to 1.12 electron volts at room temperature. So that's the effect we were talking about earlier. But that's not really the point here. The point is that these two important points in K-space are different, right? So they're not facing each other here. So what's the consequence of that? Well, first, some terminology. We get direct gap here, where there is no difference between those 2 points in K value, and then here we call that an indirect gap. Right, so now we would like to shoot some photons in. Okay, what happens? Well, the question really is, can the photon be absorbed by the valence band electrons of the semiconductor? And of course, we're already making sure that the energy of that photon or the frequency of that photon is chosen correctly. Okay, so if it has the correct amount of energy, well, the answer really comes down to how much momentum the photon carries, because we also need to satisfy momentum conservation. It's not just a question of energy conservation. Momentum also has to be conserved. So let's look at momentum for a moment. Okay, so here's my scenario. I would like to absorb that photon and bind an electron in the valence band and thereby promote that electron into the conduction band. So this is what this picture sort of is trying to communicate, right? A photon comes in, gets absorbed by this particular electron here in this state at the top of the valence band, and then that energy is manifested here, right? That electron now has enough energy to jump up to the conduction band. So, and of course it leaves behind a hole in the valence band. So here is sort of our initial state, and then here is our final state. And so what do we have to satisfy? We already said we had to conserve energy, okay? And so that means that the final energy has to be equal to the initial energy. Initially, we have a photon and a valence electron, and then finally, we have a conduction electron. So we have this kind of equation to satisfy. Just written more simply, the photon has to have exactly an energy of the band gap energy. E photon is equal to E sub g. So that is not surprising. But there's a second requirement, namely that we also conserve momentum. So the final momentum has to be equal to the initial momentum. Okay, and so written out in greater detail, we can say that initially we have a photon and an electron sitting in the valence band, and then in the final scenario, we have just the electron in the conduction band. So, and just a quick correction here, and I fixed it, forgot the h bar, right? So of course, h bar times k is a momentum. Okay, so what is the photon momentum? Well, we can go back to relativity, special relativity, and we remember a sort of a relationship between the momentum and energy of a photon that's very simple. Namely, you just multiply by c and you get the energy. And so basically our photon momentum, I'm now denoting it as p sub nu, okay, for photon, is just E over c. So very, very simple. We have an energy of about 1 electron volt. If that photon has any chance of being absorbed at all, it has to have an energy equal to the band gap energy, and so about 1 electron volt. And C here in the denominator is 3 times 10 to the 8th meters per second. And so I need to now convert that into a wave number. Okay, and again, we have this relationship. Okay, and so we get that the wave number of the photon is its momentum over h bar. And so its momentum was that, and now I'm going to divide by h bar. Okay, h bar itself is 6.6 roughly times 10 to the minus 16th electron volts times second. You can see here that the electron volts cancel, the seconds cancel. We're really just left with 1 over meters. Okay, and we're going to get about 1 over 6.58 times 3. And then if I combine these powers of 10, we get 10 to the 8th, 1 over meter. Okay, so we're talking about roughly 5 times 10 to the 6th, 1 over meter for that wave number of the photon. So this is the wave number associated with the photon. It has nothing to do with the lattice, has nothing to do with the electrons in the lattice. This is a wave number strictly associated with the photon. But we do have to compare it now to something in the lattice, right? And so the best point of comparison is where the first Brillouin zone is in K space. So why don't we compare that number to K sub BZ, the edge of the first Brillouin zone, sitting there at pi over A. So what is pi over A? Well, A is the lattice constant, and it is about 10 to the minus 10 meters, namely 1 angstrom. Okay, and so what do I get when I plug that in? Well, right around 3 times 10 to the 10th 1 over meter. Okay, so we can compare these two numbers here. I mean, this seemed like a large number, but in comparison to 10 to the 10 inverse meters, it's quite a small number. Okay, namely, it's only about 10 to the minus 4, 1/10,000th of the edge of the Brillouin zone. So it really is quite insignificant compared in the context of the lattice. It's a very small wave number when you compare it to the important scale of the problem in the lattice. Okay, and so here is our situation again from before. We're shooting a photon in, we're trying to see if it can get absorbed. Okay, and we have to conserve momentum as well. And we now realize that the photon carries very little momentum, okay, compared to sort of where the zone boundary might be on this axis. Right, so then we can say, yes, it can get absorbed very easily, okay, in gallium arsenide. But here, we would have we would have to bridge a large delta K, right? To get from tau to X, we would have to bridge a large delta K, but the photon doesn't have that much momentum. It has hardly any when plotted on this kind of scale, right? On an axis of that kind of scale. And so we have to conclude that this is not possible, okay? Not directly, not with the photon alone. So, so this is why gallium arsenide will have a very different optical properties and will interact with light a lot more easily than silicon, compared to silicon. Okay, so now let's move on to the Hall effect. Okay, so we're shifting gears, and we're going to talk about the Hall effect. Some of you, those of you who are seniors, will have seen a lot of this, and so it there shouldn't be anything new for you here. But for the rest of you, this might be your first introduction to the Hall effect. But it's actually fairly easy to describe what's happening. We have a sample, could be a semiconductor, could be a metal, and we're going to hook wires up to it, And then in addition, we're also going to subject the sample to a magnetic field, okay? And so here I have the magnetic field coming out of the page, and I'm gonna now try to force a current through the sample. Okay, so for instance, I'm gonna have some electrons traveling through here, okay? But they will experience a magnetic force, and if I use the right-hand rule, then that magnetic force is going to be up, okay? So the electrons will get deflected up as they're trying to traverse the sample. Okay, so here again is our sample, magnetic field. These electrons are, here's an electron about to go through the sample, but it gets deflected up because of the magnetic force, the Lorentz force. Okay, and so, but if there's electrons coming in, there's going to have to be electrons going out, so maybe they're going to come from a different part of the sample. Okay, and so what ends up happening then is that the net effect is we're going to get some negative charge build up at the top of the sample, and some positive charges building up at the bottom of the sample. And that, of course, that kind of charge separation will create an electric field pointing up in this case. Okay, and so we're going to quickly actually reach an equilibrium, because that electric field pointing up will create its own force on additional electrons trying to enter the sample, okay, namely down. And so pretty soon we have sort of a balance between the magnetic force trying to deflect the electrons up and the electrostatic force trying to deflect them down, okay? And so the net force will be zero on these electrons eventually, and then equilibrium is established. We get that this is sort of the equation that establishes the equilibrium, right? These two forces are equal in magnitude. Okay, and so we get this equation here. The electric field in the y direction is equal to the velocity of these charge carriers in the x direction times the magnetic field in the z direction. And so let's think about current and current density next. Okay, electrons moving to the right means, of course, a current density to the left. But such a current density, namely to the left, could also be achieved if we have some holes moving to the left. That would also give rise to the same current. So holes moving to the left, electrons moving to the right, they are indistinguishable in terms of the current that generates, right? And so let's think about what would happen if we had some positive charge carriers, say holes, moving to the left. Okay, so we have here an opposite charge and an opposite velocity vector as well. Okay, so now let's think in terms of QV cross B, right? So I'm reversing the sign of the charge, but I'm also reversing the sign of the V. So basically, I should still get a force that goes up, and that's exactly what's happening. These positive charge carriers are going to be deflected up here. We're going to get a positive charge buildup at the top, okay? And then we're going to get a negative buildup at the bottom. And now we see that this is exactly the opposite polarity. The electric field now points down, because the electric field always goes from plus to minus, right? And so now it's pointing down. So it's exactly opposite to what we had before. The upshot is that the Hall effect can discriminate between two scenarios that are normally indistinguishable. Why are they normally indistinguishable? Because they give rise to the same current. So any effect that's tied to current will not be able to be distinguished. But the Hall effect does distinguish between negative charges moving right and positive charges moving left, because it gives the opposite sign. Okay, so another way of saying that is the Hall effect can determine the sign of the charge carriers. So what charge do the charge carriers actually carry? Okay, and just take it one step further. The Hall effect establishes the existence of holes. So that's almost like a philosophical statement here. Okay, but functionally speaking, functionally speaking, you can use the Hall effect to prove the existence of holes. Okay, so let's go back to this current density, right? It's always defined as NeV, but V sub x, we said in equilibrium, was just this ratio between the electric field and the magnetic field. And so we plug that in. And so now we can solve that for the number density of charge carriers, n, little n, and we get nothing other than J times B over E times the electric field. And I can manipulate that a little bit more. Okay, the J here is the current density. That's the current over the cross-sectional area. So plug that in. And then the electric field can also be written in terms of a voltage, namely V sub L, V sub Y over L, L being the width of the, yeah, maybe I should have used a W here. Okay, the width of the probe or the sample. Okay, so therefore I get something like that. Okay, when I just bring this down and bring this up, I get this nice little formula here for the number of charge carriers, number density, I should say. And so what's nice here is that all these things that appear in this formula on the right can be easily measured. And so we can have a nice way of measuring, or we have a nice way of determining or inferring the charge density, sorry, the number density of charge carriers. Okay. So V sub Y here is called the Hall voltage. Okay, oftentimes also denoted by a V sub H. All right. We can actually solve this equation for V sub H, and what we get then is this equation. So it's maybe not surprising that the Hall voltage is proportional to the current, okay, the current density or the current, either way. If I drive more current through the sample, I'm going to get a bigger transverse voltage. So the effect increases with current. So maybe not surprising, okay, more charge buildup. The Hall voltage is also proportional to the magnetic field. That's really not surprising at all, because you need that magnetic field even to get the magnetic force, and without that, nothing happens, right? No deflection, and so that makes sense. What's also interesting here is that the Hall voltage is inversely proportional to the number density of charge carriers. Okay, so by convention, we can say that the thing here that appears in parentheses, we're going to just call that the Hall coefficient and give it the name R sub H. Okay, and so the Hall coefficient R sub H is just going to be equal to this prefactor 1 over n times E. Okay, and so since E is a negative number for electrons, then it forces this R sub H also to be negative if electrons are the dominant charge carriers. And conversely, if we have holes, then this Hall coefficient R sub H becomes positive. And if we have both electrons and holes, okay, like in an intrinsic semiconductor, then we get sort of a mixture between the two R's. Okay, we have an R that's sort of negative here, and then here's an R that's positive for the holes, but it gets, and it's sort of a weighted average where the weights are the conductivities squared. Okay, so we don't have to derive this formula, but there it is. Okay, it's going to be small. Why? Because we get sort of a cancellation, a partial cancellation in the numerator. Let's take a look at a few metals here, select metals. What I'm giving you is the measured Hall coefficient. The units here are weird. It's meters cubed over a coulomb, okay? But when you look at lithium, you get a negative 1.7 times 10 to the negative 10 meters cubed over coulomb. Sodium here minus 2.5 times 10 to the negative 10. Copper minus 0.55 times 10 to the negative 10. So these are all negative values indicating that the dominant charge carriers here in these metals are electrons. When you look at zinc and cadmium, the sign flips, which is very interesting. The sign flips, and we get a positive Hall coefficient, right? What's interesting here too is that these metals are divalent metals. And as we had already seen from the discussion before, with divalent metals, holes become important, right? Because the first band is not fully filled. We're filling the part of the second band before we completely fill the first band. And so in the first band, we have holes that can move as the charge carriers. Okay, and so, which is interesting. Now, these holes are flipping the sign of the Hall coefficient. Okay, in N-type semiconductors, also P-type semiconductors, we get a magnitude, I should say here. I'm forgetting about the sign here, but the magnitude of the Hall coefficient is much, much larger oftentimes. Like it can be as on the order of 10 to the minus 4 meters cubed over coulomb. So in semiconductors, generally in doped semiconductors, we should say we can get a very large Hall coefficient, much larger than what you would get for metals. Remember, the Hall coefficient is inversely proportional to the number density, right? So, and the measurement of V sub h can be used to determine the number density in the conduction band, or the number density in the conduction band. We've already talked about that earlier, so that's nice. And from that, we can also infer the number of donor levels or acceptor levels, right? In other words, we can infer the doping concentration. So that's kind of nice as well. Furthermore, it can also give us an idea of the mobility of charge carriers, mu. So this is the mu that we introduced earlier. Okay, the Hall effect can actually allow us to calculate that mu of the charge carriers, that mobility. So there you combine sort of the Hall voltage or the Hall coefficient with an independent measurement of the conductivity of the sample, and the combination then gives you mobility. So there's a lot of things that the Hall effect can do for us in terms of the characterization of the sample. Okay, so let's stop here. Thank you.